Hi friends, welcome to Net Talks Tamil. Today we are going to discuss about EIGRP successor, feasible successor. Already we have discussed about advertised distance and feasible distance. Now we are going to discuss about successor and feasible successor in depth in this video. Let us look at this scenario. In this scenario we have three routers R1, R2, R3. The right side is our destination, the left side is our start point, means source point. From this source point, I have the three paths to reach the destination. One is via R1, the path 2 is via R2, path 3 via R3. Now let us calculate the feasible distance and advertised distance in this tabular column. Now in this scenario, we are going to determine best path, which is a successor, and then backup path, which is a feasible successor. We are going to calculate it. Now let's create table like this: via R1, via R2, via R3. Now, if you want to, now R1 is telling to the destination, telling us the destination is 10 away. Now, this is the advertised distance, which we are learning via R1. R2 tell us it's 5 away to the source. R2 is telling from me, if I are reaching the destination, it is a 5, it's away. And then R3 is telling us it's a 9 to reach the destination via me. Okay, now we got the advertised distance of via R1, via R2, via R3. Now we have filled this advertised distance table via R1, R2, R3. Now let us calculate the feasible distance via R1 and R2, R3. Since we know our directly connected links, we can add this to the advertised distance. We will have our feasible distance. See here 10 and then connected routes having 5. 10 plus 5, 15. And then already we have 5 advertised distance, and then with that connected route having 5, 10, and then 9 is the advertised distance, and then connected having 100, so 109. The via R1 feasible distance is 15, via R2 feasible distance is 10, via R3 feasible distance is 109. The path with the lowest feasible distance will be the successor. Now here R2 is a successor, which is the least distance, that is a feasible distance, that is a successor. Now we have selected a successor, we have got the successor output. That successor will be added in the topology table, routing table in source router. Now this will be added in the routing table. Now let us calculate the feasible successor. A router can become a backup path if he is closer to the destination than total distance of your best path. I think that sounds good, right? But here let's see R1 or R3 is a suitable backup path. As per scenario, which is the second least path, that should come as a backup path. But in EIGRP case, that will not be the applicable. We have the backup path condition. Advertised distance of feasible successor should be lesser than feasible distance of successor. The advertised distance of R1 is 10, which is equal to the feasible distance of R2, which is also 10. It has to be lower, but here it's equal. It's not good enough as per the backup path condition. So R1 will not be a feasible successor. Why? Because it's equal. Equal means it is not a feasible backup path condition. As per backup path condition, it should be lesser than. Advertised distance of backup feasible successor should be lesser than feasible distance of successor. The advertised distance of R3 is 9, which is lower than feasible distance of R2. The feasible distance of R2 is 10. The advertised distance of R3 is 9. 9 is lesser than 10. So R3 will become a feasible successor as per backup path condition. Now we will be thinking it. The excellent R2 is our successor, R3 is our feasible successor. You will be find both the entries in the EIGRP topology, but you will be only find the successor in the routing table. If we lose the successor because of any link failure, EIGRP will copy paste the feasible successor into the routing table. This is what makes EIGRP as a fastest routing protocol, but only if you have the feasible successor in the topology. In this case, we have the feasible successor and successor. The feasible successor will be installed in the routing table. Sorry, successor will be installed in the routing table. If successor have any problem in this path, immediately the feasible successor will become a successor. It will take a load. Now, look closely to the feasible distance of the R3 and R1. What do you see? The metric of R3 is far worse than 1 for R2. Does it make any sense? See, the metric, if you see the successor is a 10, this R via R1 is a 15, via R3 is a 109. But it should be optimally, it should choose this, correct? But EIGRP chosen this because of the backup path condition, which is a predefined. Did you think this Cisco EIGRP engineers make a horrible mistake here by using non-optimal backup paths? No. No, it's a perfectly the way it should be. Keep in the mind the EIGRP at heart is a distance vector protocol. It doesn't know what complete network looks like. It is not a link state routing protocol like OSPF, which does have a complete map of the network. It's a purely distance vector routing protocol, only know which way to go, which vector has to go. How far away the destination is. The formula you just witnessed to determine EIGRP feasible successor is how the EIGRP can guarantee you the backup path is 100% loop free. I know this is difficult to the grasp by reading the text. Let's do the another example. Okay, how the EIGRP construct the 100% loop free topology, the feasible successor by backup path feasible successor. Okay, 100% loop free. Let us do it in upcoming scenario. Now, in this scenario, we have calculated successor, feasible successor. The feasible successor advertised distance should be lesser than successor feasible distance. The feasible successor distance, advertised distance should be lesser than successor feasible distance. That is a plain English. This is the value. Okay, for this value is either which is the less, that will become a feasible successor. Now, let's take this scenario. We see the EIGRP topology, but EIGRP does not see that what is the topology, how it is connected and all. We are looking the EIGRP topology of R3. From R3, I want to reach the destination. Let's fill this table. R3 is connected with 3 routers. All routers are running with EIGRP. R3 is connected with R1, R2, R4. Now R4 will advertise the distance to the distance network to the R3. R3 will advertise the distance network to the R1 and R2. R1 will advertise a network to the R2 and R1 will advertise the network to the R2. R2 will advertise the network to the R1. R1 will advertise the network back to R3. R2 will advertise network back to R3. It is like all will interchange their routes. Let's do the calculation. Here we have advertised distance. Our neighbors are tell us how far it is for them to reach the destination network. Next step, we'll fill the feasible distances. Here, how do we get the numbers of advertised distance in the table? Let's look all the router. R4 is very easy. R4 is very easy. The destination has a distance of 5 as seen in the topology picture. This will be advertised to R3 and placed in the topology table. Now R1 will learn the destination network through the R3 and R2. See, R1 will learn the destination network through R1. R1 will learn from R2 and R3. R3 will advertise a distance of 5 plus 4 R3 will advertise the distance of 5 plus 4 to R1. This distance will be advertised to R1. R1 would re-advertise the distance to R3 as 3 plus 5 plus 4, 12. But so, why didn't I place the 12 in the advertised distance in the field? Good question. Remember the split horizon. The split horizon rule means whatever it is received from the neighbor, or the same neighbor, it will not advertise back. See, for example, I am receiving one information from A person. I will not send the same information to A person. So that is a split horizon rule. It will do not advertise to your neighbor whatever you learn from them. R1 is not sending the information about this network back to R3. To be specific, whatever you will learn on an interface, you do not advertise back to the same interface. So what this R1 is doing here, 5 plus 4 plus 9 plus 7, 25. That value it is advertised to R3. We are received from the advertisement from advertised distance from the R1 to R3 is a 25. 5 plus 4 plus 9 plus 7. Okay, same way this R2 also doing it. 5 plus 4 plus 3 plus 7. 5 plus 4 is a 9. 9 plus 3 is a 12. 12 plus 7 is a 19. That R2 is advertising to R3. You can reach me via, okay, that feasible advertised distance is 19. Now, let's break down. Okay, R4 will advertise a distance of 5 to R3. R3 will advertise a distance 5 plus 4, 9 towards R2. And then R2 will advertise 5 plus 4 plus 9 equal to 18 towards R1. Finally, the R1 will advertise 5 plus 9 plus 5 plus 4 plus 9 plus 7 equal to 25 towards R3, which is 25. The split horizon does not apply here since R1 learned about the destination on another interface of R2. Split horizon, why it's not applying here? It is not learned via like this. Okay, it is learned via like this. Okay, so this R1 is only know about the information of R2. So it is advertising to R3. The same thing applies to the advertised distance of 19 for R2. R4 will advertise the distance to the 5 to R3. Already the 5 it will be advertised to R3. The advertised distance of 5 plus 4 equal to 9 to R1. The R1 advertised the distance of 5 plus 4 plus 3 equal to 12 to R2. And then R2 will advertise the distance to of 5 plus 4 plus 3 plus 7. 5 plus 4 plus 3 plus 7 to R3. That's what this 19 also came. Hope this point is clear. 5, 25, 19. One path is receiving wire like this. One path is receiving wire like this to R3. Now, in this scenario, R3 has learned the advertised distance from its neighbor and knows it's about one directly connected interface. So you can fill the feasible distance. Let's last step to pick our successor. The R4 is the lowest feasible distance, so it will become a successor. Okay, that's excellent. We got a successor as a 9, feasible distance as a 9. Okay, this is a less distance. It became a successor. Now, backup path we need to calculate. Let us do the feasible successor. Check if there is a backup path. In this scenario, whether backup path is there or not, we need to consider. What is the condition of the backup path? Advertised distance of feasible successor. Advertised distance of feasible successor should be lesser than feasible distance of successor. Okay, whatever advertised distance of feasible successor should be lesser than this 9. The advertised distance of R1 is 25, correct? Already this value is ruled out, is become a successor. Advertised remaining is these two. Advertised distance of R1 is a 25. Advertised distance of R2 is 19 or higher than the feasible distance of R4, which is 9. So it won't come the feasible successor. This makes sense right here. If these routers became a backup path, we would have a loop. If any of this router became a backup path, it will become a loop. It will flow the traffic here and here, here and here, again and again, again and here. If the neighbor is close to the destination, then your total path, you at least you should not getting a destination by sending packets through your router. Perhaps it is not the best path. It's absolutely 100% loop free. Because of this condition, okay, here we became a 100% loop free. Only here in condition we have only the successor, we don't have feasible successor. If we are considering anything as a feasible successor here, this network will happen with the loop. Because of this formula, which is EIGRP follows, okay, we do not have loop in this network. It's a 100% loop free network. Anyhow, we calculated as advertised distance, feasible distance, all the things. But because of this formula, this both the routes are became a useless. It will not take into the anything successor or feasible successor. Hope this video makes you clear about successor and feasible successor. If you have any doubts, please drop me your doubts in the comment box. It will be addressed in upcoming videos. Thanks for watching Net Talks Tamil. Please like it, share it, subscribe it.